Every ocean channel you have ever watched pointed the camera at the same place, the Mariana Trench. 11,000 meters, the deepest point on Earth, and every time, the same framing. The last frontier, the final unknown, the deepest place humanity can reach. There is nothing wrong with the Mariana Trench, but there is something wrong with the assumption that depth equals importance. Because the most critical layer in the ocean is not the deepest, it sits between 200 and 1,000 meters. It contains more life than any other depth band on the planet, and almost nobody makes videos about it. This is the Mesopelagic, the twilight zone. Below the sunlit surface where photosynthesis works, above the permanent darkness of the deep sea. Light enters but fades. At 200 meters, roughly 1% of surface sunlight remains. At 500 meters, the water is the color of deep dusk, a constant blue-black twilight that never changes. By 1,000 meters, there is none. No sunrise, no season. The temperature drops steadily. The water at 800 meters has not been warmed by sunlight in decades. Everything here lives in a gradient between dim and dark, and the gradient is not empty. It is the most densely populated layer in the ocean. Lanternfish are the most abundant vertebrates on Earth, not the most abundant fish. The most abundant animals with a spine. There are more lanternfish in this band than there are humans, cows, birds, and reptiles combined. Most are smaller than a finger. Most have never been filmed alive. They have rows of photophores along their bellies, tiny bioluminescent organs that glow faintly blue or green. The light points downward. From below, a predator looking up sees sunlight. From above, the lanternfish disappears against the dim glow of the surface. Counter-illumination, a camouflage strategy older than trees. But lanternfish are not alone. Bristlemouth fish outnumber them. Bristlemouths may be the most numerous vertebrate species on the planet, and they were barely studied before the 2000s. They are translucent, fragile, the size of a paperclip. They do not photograph well. They do not survive capture. Almost everything we know about them comes from acoustic readings and the contents of predator stomachs. An entire dominant life form inferred mostly from echoes and leftovers. Every night, they rise. Billions of tons of biomass moving from the twilight band toward the surface to feed on plankton. Every morning, they descend back into the dark. This is the Diel Vertical Migration. It is the largest animal migration on Earth, and it happens every single day. The entire water column shifts. Lanternfish, bristlemouths, krill, siphonophores, squid. A vertical conveyor belt hundreds of meters tall, synchronized by the disappearance and return of sunlight. The scale is difficult to hold in the mind. The wildebeest migration in the Serengeti involves roughly 2 million animals crossing a river. The Diel Vertical Migration involves billions of tons crossing hundreds of meters of open water. Every night, across every ocean simultaneously. If the biomass that rises each evening were somehow packed onto dry land, it would outweigh every living mammal on the surface of the Earth. And it would do it again the next night. The journey itself is punishing. A lanternfish weighing a few grams ascends from roughly 600 meters to the surface in about an hour. That is the equivalent, scaled to body length, of a human running a marathon straight uphill. The fish does this on an empty stomach. Empty. It feeds for a few hours in the dark surface waters, then dives back before dawn, burning a significant fraction of what it just ate on the return trip. The energy budget is razor thin. The margin between eating enough and starving is measured in milligrams. And every morning it goes back down to sit in the cold dark and wait for the next sunset. No documentary gave it more than 90 seconds. There is a reason it gets ignored. The migration is invisible. It happens in open water far from any coast in a depth band where cameras struggle. The animals are small. The water is dim. There is no single frame that captures it. Filming a herd of wildebeest crossing a river is television. Filming a diffuse cloud of centimeter-long fish ascending through featureless water is not, and the creatures that are large enough to film do not cooperate. Siphonophores live in this band, colonial organisms, chains of specialized bodies strung together into a single animal that can stretch longer than a blue whale. Some of them glow. Some of them sting with a toxin that paralyzes copepods in milliseconds. They are among the most structurally complex animals in the ocean, and they fall apart the moment a submersible's thrusters create turbulence. The ROV approaches. The siphonophore disintegrates. What arrives on the surface is a jar of fragments. What was alive at 500 meters was a coordinated, pulsing, bioluminescent predator longer than a school bus. Nobody has ever filmed one hunting for more than a few seconds. The most important migration on the planet does not make good footage. The most complex animals in this band cannot survive being watched, so nobody points the camera there. For decades, we thought this band contained around 1 billion tons of fish biomass. The number sat in textbooks. Nobody questioned it. Then in 2014, a Spanish research vessel called the Hesperides completed the final leg of the Malaspina expedition, named after an 18th century Italian navigator who never made it home. 7 months at sea, 35,000 nautical miles, a circumnavigation of the globe. The team deployed deep trawl nets alongside acoustic sonar arrays, running both simultaneously for the first time at this scale. The nets came up with expected catches. Thin hauls, mostly fragments. The sonar told a different story. Dense scattering layers, hundreds of meters thick, lighting up on the screen like clouds. The biomass was not 1 billion tons, it was closer to 10. More than the weight of every human being on Earth, multiplied by 20. The estimate had been off by a factor of 10. Not because the instruments were wrong before, because the fish were avoiding the nets. Mesopelagic fish evolved to detect pressure waves. A trawl net approaching at 2 knots produces a bow wave, a moving wall of compressed water. The fish hear it. They scatter. For decades, we dragged nets through this layer and concluded it was mostly empty. It was not empty. It was listening. The Malaspina team published their acoustic data in 2014. The lead researcher, Carlos Duarte, described the finding carefully. The paper did not say we discovered 10 billion tons of fish. It said the previous method had systematically undercounted by an order of magnitude, and the acoustic estimates suggest a biomass closer to 10 billion tons. The distinction matters. One is a headline. The other is a quiet admission that oceanography had been measuring the wrong thing, with the wrong tool, for 50 years. The response from the oceanographic community was not excitement. It was a long pause, followed by the question that changes everything. If we missed 10 billion tons of fish, what else did we miss in that depth band? The answer is carbon. Every night, fish and zooplankton feed at the surface. They consume phytoplankton that absorbed carbon dioxide from the atmosphere. Then they descend. They carry that carbon in their guts, in their tissues, in their blood. Some of it comes out as fecal pellets that sink further. Some is metabolized and respired at depth. Some reaches the bodies of predators who never come near the surface. A portion of that carbon makes it below 1,000 meters into the deep ocean, where it can stay locked away for centuries. Every morning, dead cells, abandoned mucus nets, and fecal matter drift down through this band like slow-motion snow. Marine snow. It falls constantly. If the ocean were drained and this band exposed, the floor would be covered in a thin gray blizzard of organic debris. falling without wind. Most of it is consumed before it reaches the bottom. A larvacean builds a mucus house the size of a fist, uses it as a filter for a few hours, then abandons it. The house sinks, carrying trapped particles and carbon with it. Billions of these houses are discarded every day across every ocean. Nobody counts them, nobody can. Some of this carbon reaches the seafloor, most of it is eaten on the way down. The Mesopelagic is not just a habitat, it is a filter. Everything that sinks from the surface passes through it. What gets through determines the chemistry of the deep ocean for the next 1,000 years. The ratio between what sinks and what gets recycled in this layer determines how much carbon the ocean actually pulls out of the atmosphere. This is the biological pump. And the Mesopelagic is its engine room. Forests get the credit. Trees are visible. A forest can be photographed from space. A forest can be planted and people feel good about it. The Mesopelagic carbon flux is invisible, operates at scales that are difficult to model, and does not have a spokesperson. But the estimates that do exist suggest this band processes more carbon annually than all the forests on Earth combined. The number is uncertain, the range is wide, but even the lowest estimates put it in the same order of magnitude. The highest estimates dwarf everything on land. And here is the part no model accounts for properly. This layer is warming, not as fast as the surface, but faster than the deep ocean. Temperature changes at those depths alter metabolic rates. Faster metabolism means organisms burn through sinking carbon more quickly, which means less of it reaches the deep ocean, which means the pump weakens. The feedback loop is simple to describe and almost impossible to quantify. We are changing the efficiency of the planet's largest carbon sink, and we cannot even measure by how much. We have fewer long-term temperature records for this band than we have for the surface of Mars. The satellites that map sea surface temperature to a fraction of a degree do not penetrate below roughly 200 meters. Below that line, the data is sparse, intermittent, stitched together from expeditions that happen once a decade. We are breaking a mechanism we barely know how to measure. And we cannot see it happening because it happens in a band of water where no light reaches and no permanent instrument sits. There is a reason nobody films the Mesopelagic. It is not dramatic. The creatures are small. The water is dim. There is no single animal that fits a thumbnail. No monster, no record holder, no apex predator with teeth the length of a forearm. It is a layer defined by volume and process, not by spectacle. And that is exactly why it matters more than anything below it. The Mariana Trench is a point. The Mesopelagic is a system. A point is a curiosity. A system holds the ocean together. The next time someone tells you we have only explored 5% of the ocean, ask them which 5% they mean. The deepest points have been visited. The surface is mapped by satellite every day. The coasts are monitored by thousands of stations. The part that remains most poorly understood, most poorly funded, and most consequential for the planet's carbon budget sits in a band between 200 and 1,000 meters. We have a name for it. We have almost no long-term data, and we are changing it faster than we can measure. Right now, somewhere in the Pacific, the sun is setting. And below the surface, the largest migration on Earth is beginning. 10 billion tons of life rising toward the light. No camera is watching. And at the depths they are rising from, the pressure alone would crush a human rib cage in seconds. But that is a different question.